So, hello, welcome everyone. Good morning. Welcome to this Smart Living Lunch in presence and online of April 12, 2022. It's a Smart Living Lunch seminar at the Smart Living Lab. Today we have the pleasure to welcome Professor Daia Zwicky, who is head of the iTEC Institute of the Engineering and Architecture School of Fribourg, and he will give a talk about urban densification and heightening the existing buildings in our cities. So it's a pleasure to give the mic to you, Daia, today.
Thank you, Martin, for this introduction. I should probably detail here that I'm here with a different head today. I'm not as the head of the iTEC Institute, but as a researcher at the iTEC Institute. And as announced, I will talk to you about the ConDensUrbEN project for targeting sustainable heightening of existing buildings. If that would work here. Yeah. So this is a project that was financed by HES-SO, so the University of Applied Sciences and Arts of Western Switzerland, over a period of about 3 years in total, and a budget of 200,000 Swiss francs. You can see here on the one hand, the explanation for that strange acronym. So ConDensUrbEN means construire la densification des surfaces habitables urbaines en équilibre avec la nature. So I guess you can all translate this for yourself. So, but it's how to construct the densification of urban zones in equilibrium with nature. The consortium was composed of different institutes within HES-SO. So the lead was with us at iTEC, the Institute of Construction and Environmental Technologies. I would like to point out here in particular the name of Paride Uboldi, the main collaborator working on this project. So essentially this is all his work, if you want. We had a strong implication of Transform of HEIA as well, with Stefanie Schwab above all as a lead. And we had two further members from the location in Yverdon of HES-SO. One group, Lespat, is specialized in energy and of buildings and eco balances. And the last group is associated to timber construction. So what is it all about? To give you the context, you see here on the top how the urban zones or urban regions continue to densify, which is also represented by this graph here, where we can see more and more people live in cities and less cities live in the outskirts. And we have obviously a problem in urban sprawl, as these pictures show very well how, for example, here the zone of Lausanne extended over the last, let's say, 100 years, roughly 120 years. So this is also the basis of current legal regulations, that we have to densify our cities towards the interior. How can we do that? Well, we could use industrial fallows, friches in French, where buildings are like we are here. So we could demolish everything and build very dense on this zone of the Smart Living Lab here. But as we can see also in this very zone here, probably there is better ways to work with those rooms, the spaces that are freed at the city center, so like creating parks and recreational areas, or locate a living lab, for example. So that is certainly a way to go, but how many opportunities do we have? Not that many. We could also try to reduce the surface per habitant, but if we look at the past, like shown in this graph, well, we had a reduction since the petrol crisis in the spaces allocated, but in the best case, it stabilizes. So we have always larger apartments with less people. So that's probably not so acceptable from a social point of view. What is definitely not the way to go is to tear things down and rebuild, because we're going to destroy a lot of gray energy and we're going to create a lot of waste, and that's probably not the way to go. So in our opinion, the best way to go is heighten existing buildings. I should, okay, it's gonna by itself. And this is exactly what we have looked at in this project. What is done today, you can see in this few pictures here. Usually it's like 1 or 2 stories more, maximum 3, usually built in timber or steel. When it comes to the construction of itself, the only thing that counts is money in the tendering process, obviously, while respecting requirements with regard to thermal insulation, acoustic insulation, fire protection, but the ecological impact is hardly considered. And that's what, that was the question that we have been asking ourselves. Are there other, possibly better solutions, and how to do them? So one requirement obviously is that the construction should be very light, or as light as possible, because as such we can add more floors. I have to precise, we didn't look at what is the impact on shadowing and stuff like that, but we looked at the individual building and how to construct this. And then obviously we were also interested in the question. So one thing is the financial impact, one of the 3 pillars of sustainable development, because we cannot spend that much money either. Obviously, respecting any kind of building physical requirements and structural requirements, because I should precise, I'm a structural engineer, so that's what we have been looking at. And we wanted to know, is this possibly opposed to ecological impacts of the added structure? So that's where the EN comes from, equilibrium with nature. And the general objective of this project was thus to develop generic solutions. We didn't go till a execution project, but generic solutions for the construction elements applied in heightening of existing buildings, looking at different performance requirements that are imposed on such constructions. Again, the project limits, we limited ourselves to generic constructions, considering the primary or load-bearing structure, as well as the finishings or secondary structure. From a structural point of view, we did not go to the very last detail, but we did rather something you would call a pre-design. And in this context, we already limited ourselves more in the sense of we didn't want to mix too many disciplines, in the sense of the walls are built in steel while the floors are all built in timber, because it requires 2 different disciplines on the construction site, which is usually not appreciated. And we didn't go, like I said, to a execution project, such that we did not really profoundly analyze construction details and connections, etc. But it's rather a general composition of construction elements and what is the impact on economical, from an economic point of view, so on the money side, and on the eco balance side, where we've been looking at embodied CO2 or embodied carbon above all. Also, we did not perform deep studies of building physical aspects, but for example, with regard to thermal insulation, we only made a general check of the U value and not every single thermal bridge considered. And with regard to acoustic insulation, we could frequently rely on existing catalogs that we know that this and that kind of composition does provide the necessary performance. I should also precise again that we were looking at embodied carbon in the first place. So by targeting the same U values for all the elements, that was sufficient for us to consider these constructions would have a roughly the same energy consumption. Obviously, the source providing the energy plays a major role for the whole life cycle of such a construction, but we wanted to look at the construction itself. We did not look at shading or other urban impacts of such things. We did not necessarily consider exact local conditions for how to construct it, because that may have an important effect on the tendering and the economic impact, but we rather wanted to have a relative comparison. And last but not least, we did not look at, let's say, other legal requirements for building heights very high, above 30 meters, because there the firefighter requirements change considerably. But we wanted to look at what is technically feasible. If you would work with me. No, it doesn't work with me. Hello? No. So we've been looking at this in the framework of case studies because we wanted to look at, wanted to look at concrete cases. We had to, because this determines spans and existing arrangement of structural elements that have an impact on our project. We started from the RM projects that were done by Stefanie Schwab from Transform, because within those projects, she developed, among others, construction typologies of residential dwellings, so multifamily houses from 1900 till the end of last century. And this was very useful for us because we had archetypes available with this. We did neglect some buildings with a current height above 24 meters because we thought there is not that much heightening potential. So it's a bit contradictory to what I just said, but it was to limit our choices. And from those construction typologies, we choose representative buildings as an archetype for intense construction periods. So one building from just the beginning, just before the Second World War, and one building in the period of the petrol crisis, because they present really like typical construction types and modes of the concerned periods, a typical pre-World War II building and a typical post-World War II building that are usually found in different zones. Like the first one is rather at the city center. We have typical construction with massive walls, hollow block slabs, and another use of the what is it in English? The ground floor. So there are usually shops and other things in those zone, and above is residential. While the second building is a typical standalone building, rather in a suburban zone with multi-layer walls, concrete slabs, and garages at the ground floor. So this first case study is called Bord. And you can see here we have this hollow block or hurdi slab that only span in one sense. Essentially, the walls are made of cement bricks. And we already came to the conclusion quite early that we will have to, we assume, demolishing what you could call the penthouse. It's usually a little bit smaller than the rest, and the attic, and we construct from there upwards. The first thing we have been looking at is what is the capacity of the existing structure with the target that we can identify approximative surface masses of the added floors, because they may definitely or will definitely have an impact on the materializations of elements that we can apply. And we wanted also to know, do we need strengthening of the existing structure, Or to make it even more detailed, like if we applied punctual some strengthenings, would that allow us to add 1 or 2 more floors? So that's the idea behind that. We took into the consideration, obviously, the existing floor plan, and we admitted it that we simply copy paste this for additional floors so that we do not fundamentally change the structural system yet, but wanted to know how many floors we can add, or respectively, what is the dead load per floor that we can allow if we add 1 floor, 2 floor, 3, 4 floors, obviously considering a certain life load. And you see this dramatically, this mass or admissible dead load per floor obviously reduces dramatically with every floor added. And still at 4 floors added, we can still have a surface mass of 5 kilonewtons per square meter or 500 kilogram per square meter, which is already quite comfortable. We could also find out in that study, confirming former results, that the existing building is already insufficient in its current state for earthquake requirements, and will as such would require strengthening anyway, a certain basic strengthening required. The second case study is this standalone building, typical from the 70s, with the walls made of clay bricks, the slabs made of reinforced concrete. Reinforced concrete allows us to admit a load carrying in both senses. Again, we assumed that the attic, which is currently non-residential, obviously, shall be destroyed, and we copy-paste the existing floor layout for how many floors we can add. We applied the same approach, and we can see if we look at the load carrying capacity of walls for vertical loads only, we can add quite a few floors and still have, like adding 4 floors, still having 200 kilo per square meter for the dead load admissible. But if we look at the combined efforts acting on the stabilization structure, so the walls from dead loads and wind, we can essentially add 1 floor with a quite modest admissible dead load. This is associated to the fact that if you wish, the earthquake acts here where the center of mass is, while the reactions act there where the center of reaction is, and this torsions the whole building and loads the walls additionally. That's why those loads are so low. So we can tell from that we can or add very few floors, or we need to apply strengthening, be it for wind, be it for wind loads, be it for earthquake, to add more floors. But this gave us a first idea what we're talking about, how much dead load can the slabs above all can have, and associated materializations. So we're now looking more profoundly on the elements of this heightening structure. There are many requirements to be considered. So we have structural requirements. We need sufficient strength. We need sufficient serviceability, so that, for example, floors do not deflect too much or they feel like a trampoline or something like that. So this requires some minimum thicknesses already. We need to meet certain fire protection requirements. To protect not the building from fire, but the inhabitants from fire. And we have those building physical requirements with regard to thermal insulation and acoustic insulation that has different sub classes, like for impact noise, airborne interior noise, and airborne exterior noise. So all this has an impact on the compositions of our elements that we have to take into account, and which have above all, or many times, they have a strong impact on the secondary structure. And this is a little bit, unfortunately, a little bit the poor child of construction projects. It has an enormous impact, but it is hardly considered, as you will see later on. So we have been looking at different floor plans. This is the board building again, where we came finally. I already tell you that conclusion. We came to the conclusion we can essentially use this building to reproduce everything. So these are the two buildings, Board and Cossonay, and the first thing was that we stay very close to the existing floor plan because this limits spans and it has only small changes in the force flow as a consequence, but we have rather limited choice in the apartment layout. So you see here, this is what the new apartments of the new floors would look like. It's more or less the same, and the same goes for the other building. So not very generous rooms, not very generous apartments, but something that fits as close as possible to the existing structure below. We also have looked at what we called an open floor plan, where only core and facade walls would be considered in the loading system. So you see here superimposed, like we have really large walls that collect all the forces and bring it down to the existing structure and further down to the soil. Obviously has a consequence as a significant changes in the force flow, but we gain a lot of freedom in the arrangement of apartments and can provide something that is more appropriate for current times. And the same goes for this other building. These two reflections, or these reflections on the floor plan, they essentially consider architectural requirements on the one hand, and above all, they gave us an idea of what are the spans that we are talking about. We found out then that the first building I've introduced, the Board building, was worse in the sense of that it has the larger spans. It requires quite important what you call deep beams, mur voile in French. So it's a beam that has the height of a whole story and can collect a lot of forces and bring it down to the foundations and further. You can see this here. This is this is a deep beam in this section here. So it is a structural element that carries over large distances and can accommodate quite important forces. As a consequence, we could see that in the one building, we have a maximum span of approximately 11 meters. So we're approaching footbridge spans here already. And the other one with 8 meters, which is quite important as well already, again. So this gave us an idea of what are we talking about in terms of slab spans, and was a necessary basis to do the structural pre-design of our construction elements. We have been looking at many different materializations of slabs and walls elements. We could categorize them in the sense of that we have elements associated to concrete construction. It's quite intuitive that you will not pour very heavy concrete to construct these additional floors. Still, it is like the reference of what you would do when you construct a new building. And that's why we wanted to consider it. The same goes a massive slab, but this time using lightweight concrete, or then we have voided elements like with hollow blocks or pre-stress and voided. So all these elements had to be structurally pre-designed to know what must their thickness be. We have then also pure steel construction, what we call CFS, cold formed steel. These are very thin steel elements, so it's extremely light, but very sensitive to stability. And that's why, for example, here you need to add a timber plank that stabilizes those elements. Further going to composite construction, so where we mix different materials in relatively typical ways, like using steel elements in combination with concrete slabs that provide additional stiffness and strength. We could find such proposals in the literature either that we have cold formed steel elements that are insulated or made light with a hollow block made of insulation material, but still adding concrete for additional stiffness. It's a, let's say, commercial system called coffradal. And then we also wanted to look at something a bit more exotic. So we took glass fiber reinforced polymer elements that look a little bit like steel, but weigh maybe 20% of steel and do not provide the same stiffness, should also say, and made them composite with lightweight concrete. And then obviously also considering timber-based construction, where we used classical elements like such multi-box elements made of massive timber or glue lam, so glued laminated timber, looking at more recent ways to construct in timber, so with CLT, cross-laminated timber. So they have planks in both directions and can also carry load in both directions. And for larger spans, we had to do a combination of them. All the slabs were considering a secondary structure as required to meet all the building physical requirements, above all with noise and fire protection. And the roof was essentially the same element as every floor element, unless that we added the necessary thermal insulation as the roof is part of the thermal envelope, obviously considering this constant and given U value that we wanted to attain. So roof, same as a slab, sorry, floor slab, but with insulation. And then we had to dimension all this, obviously, for the variable spans. You can see here an overview as it gives you an idea what we are talking about in terms of depth of the total element, in terms of dead load of the total element, and this obviously to be combined with what can we add. And you can see we can go from something really, really heavy in regular concrete, so almost 1.3 tons per square meter. So that's a regular car per square meter as a dead load, which is extremely heavy, to something very, very light if we construct with these cold form steel elements. We have been considering spans going from 7 to 11 meters. We essentially considered simple span slabs because we have many unidirectional elements. So like such an element here that has one loading direction or one load carrying direction. We apply or also elements like these, they carry in one way only. It was only for elements made of massive concrete that we considered a certain contribution in both sense or also continuous. Obviously in the structural design, all the requirements that are imposed for serviceability and strength, plus adding all the necessary layers for satisfying building physical requirements. Something similar we did for the walls, again in different categories: concrete construction, steel construction, polymer construction, or timber construction. We looked at regular constructions like massive walls made of normal concrete or lightweight concrete. We also looked at prefabricated panels that incorporate a insulation made of EPS, but also looking at ultra high performance concrete, so with the objective to make those elements even thinner. Because this is something I should have probably mentioned at the very beginning. If you want to construct very light for your heightenings, you can do it in two ways. You can take regular dimensions or usual dimensions of or with light construction materials, so let's say timber as a light material in a regular dimension of, I don't know, 20 centimeters. Or you can take much heavier materials, but higher performing materials and make very thin elements. And as such, the mass in all is comparable. And that was exactly the way we have looked at it in the context of these conceptual designs for those different materializations. We also had to add some non-structural walls, but there we made our life easy. We considered one type of composition for internal non-structural walls and another type of composition for external non-structural walls to not make life even more complicated. Because in the dimensioning, we had to take into consideration so many requirements, above all for the walls. We have this acoustic insulation requirement, thermal insulation, if applicable, fire protection, structural function, which is also a function of what floor plan do you choose. And the number of combinations became so important that we had to limit ourselves a bit further. So we did essentially a structural design for adding a maximum of 4 floors. This should be compared to the usual height of buildings of today. So buildings of today, they usually have like 3 to 5 floors. So we essentially double the existing height, which is, I think, quite important. And that's why we could limit ourselves to this. We have walls that carry above all vertical loads. So you don't have to be able to read this agenda. It's simply to this legend caption, sorry. It's simply to point out what are the different requirements applicable to those wall elements. There is noise protection, fire protection, so many things, and you need to consider these with designs on the one hand, but also with constructive measures, so like the secondary structure. So we have walls that carry mainly vertical loads only, but then we also have these deep beam walls like the one here or the one there that catch a lot of the additional loads and have to bring it down to the existing elements. So for the compression walls, it's relatively easy. You look at it as if it was a column that is 1 meter wide, and you design how you must design as a structural engineer. I don't bother you with those details. But more interesting are the deep beams, because they have to bridge quite important spans. And we wanted to look at different materializations, like I said. So concrete walls that you usually design with such strut and tie models. Steel walls were constructed as a truss, so we could hide diagonals inside to have the necessary structural system. When we did it in glass fiber reinforced polymer, this is also something that we looked at in an earlier project. How can we make this load bearing if we like bolt panels on GFRP profiles? Structurally, it works. So we also considered this approach, or last but not least, a massive timber mall made of cross-laminated timber for the different construction modes being associated to the main construction material. Then we also had to look at what you call shear walls. It's the walls that stabilize your building for wind and earthquake, and above all, at the existing shear walls. So I already pointed out that the existing shear walls already require strengthening in the current state of the building. It's always a question if the intervention is proportional or not. But if we're gonna add floors, then the intervention definitely is proportional. And you can tell already from this diagram here that if we add floors, we also add like earthquake forces and wind forces, and they will necessarily load the existing shear walls in addition. And so we wanted to know to what extent we need to strengthen those shear walls, because those interventions are at the load of the heightening, so to say. This is obviously a question of what kind of construction do you add for the additional floors? How many floors do you add? So we had to bring that a little bit further down, simplify it a little bit further. That's why we said we're only looking at two different categories of strengthening, like we're gonna add a light strengthening or a heavy strengthening. Heavy is easy. We take the existing wall as a lost formwork and we simply concrete the new reinforced concrete wall against it. It's done in practice. It's not something we've invented. And there you can accommodate roughly any kind of earthquake or wind load you want. No problem, because you add an element. Based on a former research of ours as well, we looked at strengthening of brick walls using glued carbon fiber tissues on these walls with different layouts, so like only vertical strips or adding diagonal strips, etc. And from this, we could identify, okay, it's no problem at all to increase the available resistance by 50 to 70%. And that's what we considered a so-called light strengthening. This has to be associated to reflections from earthquake engineering, like what is the current exploitation rate of the element and where do you need to get that? I think it's a very structural engineering issue, so I don't bother you too much with that. But we could, thanks to such reflections, we could identify as a function of the exploitation rate, so to say, do we need to use light strengthening or heavy strengthening? And then obviously with the surfaces concerned. If you want more details about this, I'll be glad to explain it further at the end. And the same we did not only for earthquake, but also for wind loads, considering 2 or 4 added floors. So this allowed us to identify how many elements do we need to strengthen. Now, these slab elements and wall elements, they need to be combined to construct the new floors or the added floors. And there would be an almost infinite number of possible combinations. If you say, okay, these are all the slab types we've looked at, these are all the wall types, and theoretically you can combine any one with the other. And well, we had a comfortable budget, but not as comfortable, so we had to limit ourselves down. Everything that is in red, we said we're going to exclude those because we consider this inappropriate discipline mixes. To give you an example, we're not going to put CLT slabs on a steel wall because it's combining 2 different, let's say, specialists or construction companies, but this is what we're excluding. Everything that is in yellow is what I would call an unwise combination. So why should I use like a lightweight concrete slab, but then put it on a regular heavyweight concrete wall? Doesn't make that much sense. Right? So this allowed to exclude some more. And in the end, it's the green ones that we've been looking at because we thought, okay, these are reasonable combinations. What is blue would also be thinkable, but we thought, well, we probably not got much more insight if we analyze those cases as well. It's still enough cases to be analyzed in our view. So these green combinations were those that we have analyzed. Just as an example, obviously a CLT slab on a CLT wall, or then a steel concrete composite slab on a steel wall, and or combining, for example, GFRP slabs with GFRP walls, things like that. So the green ones are the combinations that we've been looking at. Sure.
Just quickly, sorry to interrupt. It's fairly obvious that you mainly on the diagonal of the matrix. With one exception, the green and the bottom left insit something about this choice.
Yeah, this is sure. So the question was, we seem to be obviously quite much on the diagonal. And why is that the case, and why we have some outliers? Well, it's a pure incident that we are on the diagonal. Well, no, not such pure incident, but we have like here, concrete construction, they more or less go together. We have here timber construction, and here timber construction, they also go together. And we've been looking at the outliers, so to say, that we thought, okay, here we have rather lightweight regular concrete construction, and it would make sense to combine them with lightweight wall construction because elements are thin, or we even combine it with even higher performing concrete and thus thinner elements, and that's how the outliers can be justified. Was that a reply to the question? Very good. Okay, so these are the combinations we've been looking at. In terms of evaluations, we know that, okay, we satisfy building physical requirements, we satisfy structural requirements, and we wanted to evaluate what is the impact of those combinations on construction cost and on ecological impact or embodied carbon. The construction cost, we did it rather in a qualitative way. So to say, we took the material quantities and we multiplied it with usual unit prices per material and added something for the mounting of the whole thing. This is quite approximative, obviously, because the effective construction cost will be very much impacted of the specific site locations, access, where can you put the crane, can you put the crane anyway, etc., etc. But we wanted to compare those materializations qualitatively, and that's why we did, on the one hand, a normalization to our reference, which was in our case timber construction, which is usually done today. So is the other solution more costly or less costly than timber? Or then we did it within the same material. So it's a relative evaluation, so to say. The embodied carbon, we looked at more detailed. We looked at it per construction element already. So we have the slabs, we have the walls, different type of walls and roof. And we subdivided the composition of every element in principal categories. So usually you have like an exterior layer, a low carrying layer, and an interior layer, or an upper layer, low carrying layer, and an inferior layer. You can call this, we have a cladding layer, a structural layer, and a finishing layer. So what you see from inside, what you see from outside, and what it's been in between that carries the load. We looked at a global warming potential according to the KBOB database, but we did not have values available for all the materials that we've been looking at, and that's where the specialists from LESPAT came in, because for the non-available materials, they could provide estimations for those impacts either. We did not look, again, on exploitation energy, but only embodied carbon for fabrication and elimination or demolition. And obviously, all the different layers and material consumptions have to be amortized over a certain period, but also there are directives available in this technical bulletin. And obviously, we had to consider if we add one, two, three, 4 floors, and that's why we normalized everything to the energy reference area, which includes the last existing slab because it's the new residential slab. So that's integrated in that. Now, finally, some results after all these explanations. Here you can see the results for 2 floors added with a restrained plan. I'm totally aware that you can read nothing, but I'll give you some explanations. So you can see for one certain materialization, you can always see there is 2 columns, and with a bit of variation, this is associated to different kind of secondary structures that you could add that satisfy the same requirements. So this gives us a range already. We can also tell from the colors, you can tell the highest impacts are hidden in the slabs, followed by the roof, and then the interior walls. To give you an order of magnitude, the reference is timber with 5.1 kilo CO2 per square meter and year. This gives us the minimum eco balance, which is followed by cold formed steel construction, which is relatively close either to that, which is the lightest one, which is down there. But still, it's already 290 kilo per square meter. It's supposedly very light, but yeah, not that light as you thought. Huh? All the other solutions, except for the GFRP solution, which is the total outlier above overall, they are relatively close to each other. So we can say, if we want, instead of using timber, we are using concrete, we add like 20 to 45% in embodied carbon. If we use steel-based solutions, it's like 15 to 35% that are added, obviously considering the maximum in secondary structure. The great exception is GFRP-based construction that adds almost double of the embodied carbon. If we now compare it between the different combinations, so you have on the horizontal axis, you have relative cost, and on the vertical axis, you have relative embodied carbon. Down here is the reference, that's the timber frame structure, that gives us the origin, and the others are normalized to that. CLT is relatively close to that timber frame solution, only costs a bit more, but same ecological impact. Lightweight concrete-based construction may be a little bit cheaper, but is much considerably worse in embedded carbon. So overall, we can say concrete solutions, they add 20 to 40% in, roughly speaking, in embodied carbon, and can vary between -10 plus 10% in cost. Steel, similar order of magnitudes, but as a tendency more expensive. And the worst, obviously, somewhere up there, GFRP based, doesn't make sense, even though it's quite a light solution. So if you look at money, choose lightweight concrete. If you look at eco balance, choose timber. If you want to be as light as possible, choose cold formed steel. If you would do the elements some kind of rawer, so you can omit certain finishings and claddings, then you can still reduce the impact by up to 15% in both senses, cost and embodied carbon, so non-negligible. But you will live with a rawer element. The question we asked ourselves as well, is there possibly a connection between the material used and its self-weight, its density, and the ecological impact? And as you can tell, no, there isn't. Not at all. So this is increasing mass, this is increasing ecological impact, and obviously there is no correlation at all. But it's the overall weight that plays a role in that. Same for a heightening with 4 floors, just the most important results. We have a little bit of increase in the mass per square meter. The relative impact of eco balance is reduced. Obviously, you add more floors, so overall you add more embodied carbon. But that's associated to the fact that the energy reference area is increased. Still, the highest impacts are in the slab, but now followed by the walls and then the roof. And using raw elements would result in a more pronounced reduction. We can say here also other solutions than using timber. We can say the eco balance is simply increased and the cost remains more or less constant. We can tell from this figure, this is like for 4 floors, heightening as much as possible is good, is favorable, because it reduces the relative cost impact and it reduces the relative embodied carbon impact, and it's also favorable if we further consider refurbishment of the existing structure, because then we can do like some cross financing if you want the additional floors or the the rent from the additional floors can pay for refurbish the existing building. So that's why it's interesting to add higher as high heightenings as possible. Same kind of results for 2 floors, but now with an open floor plan. So obviously the scales are a little bit different here. Rather, the same conclusions, highest impacts are stored in the slabs, followed by the roof. The minimum embodied carbon is a little bit lower. Again, timber, followed by steel concrete composite construction. And the timber solution is also the lightest solution at the same time. So you can see here the percentages that are added in terms of eco balance if you choose another material. So it's still, say, comparable order of magnitudes, but differences are available. So as we have an open floor plan with large spans, it requires timber box elements, and the deep beams using an open floor plan, they need to be in CLT anyway, and this is also the lightest solution as I just mentioned. With regard to relative impacts in construction cost and embodied carbon, the differences are less pronounced. So this, again, the reference here is the timber construction using box elements for the slab. CLT is essentially equivalent using CLT. Lightweight concrete, again, maybe some economic savings, but that probably dilutes in the precision of our calculations, but we can tell for sure that it will increase the embodied carbon. So anything else than timber will result in a more pronounced embodied carbon impact, plus 20 to 45%, except for GFRP that is out of the race anyway, in comparison to the other materials. So we can see we can have a very little gain in economic impact. Still, if you want it as low cost as possible, lightweight concrete, as most as ecological, sorry, as possible timber, as lightweight as possible timber. All other solutions are worse in ecological impact. If we would use the same for 4 added floors, the reductions are less important, but conclusions remain the same. So where do those impacts hide? We have seen first in the slabs, in the roof, and the interior walls. Don't bother to read anything on these figures. It's what we could find in the slabs, the most important contributors to embodied carbon. If you use a rather massive or heavy construction, the impacts are mostly hidden in the structure, while if you construct very light, so cold formed steel or timber, it's essentially in the cladding and finish. But the sum of those may result in comparable impacts. For the roof, it's above all the cladding, including the thermal insulation. So optimizing that thermal insulation material would probably be a good thing to do. And for the interior walls, it's essentially in the finishings, except for timber and steel. It's essentially in the structure, except for timber and steel, where again, it is in the finishing, so similar to the slabs. We could always see in those evaluations that the strengthening measures that we apply have a very modest impact in comparison to the added floors in terms of eco balance, and they definitely improve the existing building. So to finally conclude, I'm always talking since a long time already. So the taller the heightening is, the more favorable it is. But the taller you go, the more compromises you need to do on the floor plan layout. You cannot do the open floor space and add like, I don't know, 8 floors. That's not really possible. Oh, well, it would be possible, but you do a lot more important interventions. The floor plan and the floor number obviously have an impact. If you use a rather open floor plan, it's architecturally definitely more convenient, but it's results in longer spans, so you need lighter construction. And that's why I would recommend going for steel or steel concrete composite construction, hollow blocks, CLT, or then if you use timber box, pre-stressed concrete or sandwich walls, they can be applied for any kind of combination of floor plan and floor number, but the number of floors should be limited to roughly 3. There is no simple answer to the question, which is the most appropriate construction material, main construction material. There is really no obvious answer to that, but I think the most important is think of what volume of a material is used and what its unit embodied carbon, and the product of that is what matters. The governing elements are slabs, roof, and interior walls, and the impacts of cladding and finishing may be very important. And so this should be looked at, and don't try to optimize the structure. So last but not least, recommended materializations. So two floors added is a modest heightening. If you use this with a restrained floor plan, go for timber, possibly for cold formed steel if you want to be as light as possible. If you want to be as economic as possible, okay, you can do that with lightweight concrete, but you add 30% embodied carbon and you triple the weight. Same maybe to round this up, if we look at 4 floors with open floor plan, the most ecological solution is using timber. It may be a little bit more costly than other solutions, but it is also the lightest way of constructing. And if you want to be as cheap as possible, you would rather go for pre-stressed concrete void slab in combination with high performance concrete sandwich elements, but you will have to live with 30% embodied carbon added and 120% weight added. So there are different combinations possible, and it depends on the target that you set yourself. Does it have to be as ecological as possible, as light as possible, as cheap as possible? And then you come to another conclusion. Future research needs, I think that's more or less the last slide. Obviously, it would be interesting to look at developing those concepts using deep beam walls in heightenings further and to deduce generalized concepts, obviously in interaction with the existing structure and possible strengthening of the existing structure. So that would be definitely interesting in terms of architecture. We would also have the need to do structural and construction details for all those elements that have to be connected somehow, one to the other. They may have impacts because they may change the dimensions. So they may have cost impact, embodied carbon impact, weight impact. Now, weight maybe not too much, but also building physical impacts, so thermal bridges above all. The evaluation of construction cost would also be interesting to look at governing combinations here and really develop it to tendering level. And then we could see more precisely what, if our evaluations were more or less in the target. And with regard to construction materials and elements, we could also deduce an important impact is in cladding and finishing. So if we, with any layer that we can avoid or that we do avoid, we gain in embodied carbon. That's definitely a thing to go. Or then we should try to target more mono-layer elements that you do not have to add many layers, including their connections, which may possibly also require developing construction materials that are not available yet. So like my famous wood-based concrete, for example, but that's just a parenthesis. And with that, I will thank you for your attention. And I would particularly like to point out again the core members working on this project, Bari Deoboldi above all, Sebastian Lasvo from Lespad, Stefanie Schwab from Transform, and Andrea Bernasconi for everything with timber construction. Thanks a lot. Sorry for being so long.
Well, thank you very much, Daia. If you have any question, you can use this microphone in the way that people online can hear the question. I just send a message also in the chat to invite people to ask questions online. It's not the case. So, anyone?
Yes, thank you very much, Daia, for your presentation. I have first one question about the method. You did consider two options for the heightening. One is the continuing the existing floor plan. The other one is this idea of deep beams. Normally, if you read in literature, there is a third solution, which is consists of how do you say that? A sort of a load distribution platform that you put above the thing. Why did you not consider this solution?
Load transfer slab. Yeah, that is a possible solution. The issue with that is these are elements that are usually really massive in dimensions. It is often done in concrete, at least in new construction, because there you have a similar approach. Or then you have a really complicated construction of made of steel, probably. Well, we just thought it's maybe not challenging enough to simply say, okay, now we have a slab that distributes us everything as we want. We also thought it adds a lot of height, not unusual or not useful height, but we wanted rather to exploit the existing elements as good as possible. And yes, it's obviously it is a third solution. You can do that, but we thought that the deep beam approach is more promising.
May I ask you another question? You said that for your conclusions, there is no evident solution that is, or no evident material that is the one you would choose, because you consider also economical factors. But if you look from ecological point of view, I think it's quite obvious that the timber solution is the best solution, and especially if you combine the idea that timber for some walls, like just behind you, you can use them without further cladding inside. This needs special maintaining during the construction, but I would, from an ecological point of view, and I think it's now really important to reduce this carbon impact of construction, say that there is a clear recommendation to do this kind of constructions in timber.
I entirely agree. I totally agree. If you look at embodied carbon only, then it becomes obvious that we're going to do timber. It always says timber, 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 timber. The issue, or not, and that's not an issue. I mean, everything with regard to economic impact, this will fundamentally change when embodied carbon is finally taxed, and then timber is even more at the forefront. That's obvious, because I mean, you see the additional embodied carbon that is added, like a third or almost half of a timber construction. So then it's not the most economic solution anymore to use lightweight concrete or pre-stressed concrete, obviously. But this is not a regulation that we currently have. And a project developer is, unfortunately, for the time being, still not that interested in the first criterion, but rather interested in the two following ones.
I agree with you, but another way, I agree with you that this is the case, but on the other hand, we are the ones that promote this future habitation, and I think we should really promote these more ecological solutions.
Yes, I entirely agree. I mean, if you look at these are even more rounded values, obviously, yeah. But just to have an idea in the order of magnitude. So if you want to be ecological, you use timber, period, and you live with maybe something that is 10 or 50% heavier than the lightest solution, and you live with an impact on the cost of 5 to 10%. And this is probably the way to convince project developers that you say, look, if you do it in timber, you're clearly the most ecological in terms of embodied carbon. You own that the consequence is it costs a bit more and it is possibly a bit heavier. I agree. I totally agree.
Thank you for your presentation. I have a question about how general the result is. It just works in French-speaking area, or it works for entire Switzerland, the result?
I mean, sorry, I didn't get the beginning.
Okay, how general the result is? Yes, it just works in French-speaking area in Switzerland.
Ah, okay. To what extent this can be generalized, huh?
Yes.
Well, the periods with intense construction activities are comparable all over Switzerland, I would say, maybe 5 years more or less. Huh? The type of construction applied can also be found more or less in whole Switzerland. There are always particular cases, like, I don't know, in Wallis, they work more with a chalet type of buildings, and in another zone, they use more concrete because there was a big construction company there. But in terms of materialization of the existing structure, it's quite comparable all over Switzerland, I would say, or at least on a larger region than maybe just French-speaking Switzerland. And the materials proposed for the heightening, they're available all over.
Okay, and for the case study, the case you collected, it is distributed in all Switzerland or only located?
I get it, yeah. It is rather, don't look at it as the specific case study, but look at it as a construction archetype.
Okay.
And that construction archetype can be found all over Switzerland, or those construction archetypes.
Okay,
yeah.
Thank you.
Thanks, really interesting the presentation on the topic. I was wondering, based on this, about the archetypes, like if these results maybe can change if we consider the other archetypes, like more modern buildings or more ancient buildings, or anything of all this would be different in that case, or you, and also from your experience, I see that you only consider 2 of them because it's limited the study. But from your experience, what would you say?
I would say it's not my experience, it's the experience of Stefanie Schwab. But I think with the 2 construction periods and the associated archetypes that we've been looking at, we cover the major half of archetypes of buildings that have been constructed. This can obviously be detailed even further. There is exactly such a project going on with Stefanie and Milen, but they look at the renovation of the existing building stock. but they collect a whole lot of information on the constructional and structural archetypes they have. And well, obviously there are buildings that have been constructed before 1900, but this is such a small percentage in comparison to the rest. We can say, okay, these are monuments that we cannot, that we have to touch differently anyway. And you forget about heightening them. It will not be accepted in any case. But we want to look at the large majority of buildings. But please speak to Stephanie Schwab. She can give you a whole conference on that, or will be able to give you a whole conference on that.
Thank you, Daia. So I'm really glad to hear that there are still a lot of collaboration between architect and engineer with your results, and especially the fact that, if I understood well, if you add, for example, it's easier to add some floor, some extra floor, but the constraint on the design on the rooms are quite heavy as well, like the
it is always a compromise.
Yeah, and
if you want to have, sorry, you didn't even ask your question yet.
No, but that's something that I was quite interested, that if we want to have, for example, a good ecological bilan, maybe for the architects, the design of the extra floors are quite important, and we have more constraint than if we have an ecological footprint more important, if I understood well. Like that we are more free, like the design of the floor is not that free depending on the structure we use. I was quite interested by that.
Okay.
Where I feel really like the architect and the design of the space is entering in the question. I don't remember where you.
I don't have that with me.
But you mentioned that.
Yeah, I was looking.
Anyway, they are constrained about the design inside the new apartment or the new floor. And if we have like, yeah, it's just maybe there that if we have more, if we have not an open plan, yeah, it was about open plan.
Yeah, yeah. I mean, if we have such an open floor plan with very few structural elements inside here, we can more or less do what we want, and we can subdivide it as we wish, and so we can provide room sizes that are appreciated today. But there is an impact on the existing structure, and there is above all also an impact on the elements of the heightening. And so it's always a compromise. You have to buy one thing with another in the end.